Good morning, dear guests, dear participants, esteemed speakers, and welcome to the EUROLAB Eurachem webinar on how to validate measurement procedures, including sampling. Today, high-level speakers and authors of the new guide, VaMPIS, will provide valuable insights into the key best practices for validation of measurement procedures that include sampling with specific examples and guidelines. All participants today here in our webinar have the opportunity to address questions and to further clarify any possible uncertainties directly linked to the guide with our authors and experts in the field during the roundtable discussion that will take place at the end of our webinar. In case you have any specific questions during the presentations, you can always address them in the chat box. During the webinar, we would kindly ask you to keep your microphones muted so we avoid sound interferences with our speakers. And this webinar will be recorded, and the recordings will be made available on the Eurachem YouTube channel. With this being said, I would like to first introduce myself. My name is Laura Martin, and I'm the Secretary General of EUROLAB. And now I would like to provide you with some few insights on what we are doing in EUROLAB, who we are, and some of our projects and activities. With this being said, I will quickly share my presentation. Can you please confirm that you see my slides?
Yes, Laura.
Perfect.
Not
I will
yet
put
in
them
presentation
in presentation mode.
That's it.
Thank you very much. EUROLAB this year has the anniversary of 35 years. We have been created since back in the 90s, and we have various members in Europe and beyond. In terms of our activities, in the Secretariat that is based in Brussels, we provide a wide range of activities from research to drafting and participating in European projects. We are engaging with various European institutions and key stakeholders. We are publishing specific technical documents and guidance documents. We are very active into monitoring European legislation and working closely with various representatives from the European Commission. We are positioning the laboratory and conformity assessment community on a European level. Last but not least, we are organizing various events and trainings. In terms of our priority areas, they are very important because we develop our annual action plan according to these priorities. For 2025, we have developments at the European level in terms of legislation when it comes to sustainability, Green Deal, food, medical devices, energy, and specifically energy efficiency for laboratories, metrology and calibration, accreditation and standardization, Laboratory of the Future, very important, with topics covering machine learning, digitalization, cybersecurity, robotization, last but not least, usage of artificial intelligence and blockchain technologies. European quality infrastructure is also a very important topic on our agenda for this year. Our technical work in EUROLAB is done in the EUROLAB Technical Committee on Quality Assurance and the specific 4 working groups dedicated to digitalization, sustainability, accreditation and standardization, and publication of specific guidances and technical reports. Important to know, these working groups are open to all the members, non-members, experts from the field. In case you are interested, you can contact us. EUROLAB publishes various guidance documents such as the cookbooks, which are available on our website, and they are guidance documents for the implementation of the 17025 standards requirements. We also have technical reports, for example, the technical report for management of digitalized systems in laboratories according to 17025. The guidance document technical report are all available on our website and you can access them for free. We also work very closely with various stakeholders that are active in various fields related to our activities and priorities. You can see European organizations as well as international organizations active in accreditation standardizations, metrology, legal metrology, conformity assessment, and many more. We also work very closely, as I mentioned, with the European institutions, and we are also active in various technical committees of European accreditation, ILAC, ISO. We are also members of the European Quality Infrastructure Network. That is an initiative that was set up by 5 main organizations active in standardizations and Senelec accreditation, EA, metrology, Euramet, and legal metrology, WELMEC. Also currently, ProSafe for surveillance organizations are also part of the network, and EUROLAB is representing the conformity assessment field. We are also organizing various trainings and seminars. The upcoming important seminar will be organized with our Italian member ASOTIC, will take place in September in Torino, and will be focused on certified reference materials. In case you are interested, you can scan the QR code. We are also partnering with various other organizations such as IMICO for the organization of international conferences. One of them will take place as well in Torino, and it will be dedicated to certified reference materials, digitalization in traceability, digital twins, quality management and conformity assessment, and many more. We are very much active in European projects. One of the projects that we are working on is the Screen Food project, dedicated to food safety and metrology for food safety in a circular economy, targeted and screening methods for contaminants in food and recycling packaging. The project is funded under Metrology Partnership of Euramet program, and we also have a stakeholders committee that you can access with scanning the QR code. We also have various other projects that are in pipeline submitted under Erasmus Plus funding. One of them is dedicated to green labs, the other one to digitalization for laboratory experts. We have various publications that you can have access to if you would like to be added to our mailing list. We are happy to do that. And we are very active on our social media, LinkedIn account, and on our website. My last minute will focus on our new evolutionary strategy that has as main aim to enlarge the EUROLAB organization by mirroring the already existing structure of our national members. With the new strategy, our main aim is to provide also opportunities of other representative in conformity assessment sector to join directly EUROLAB. Our main pillars will be continue to be inclusiveness, democratic organization, open and sustainable through various, of course, specific internal rules that we are going to revise. And the main key categories of membership will be the national members, active members, with the national organization of conformity assessment bodies, being it laboratories, inspection, certification bodies. We will have the sectorial members that will be dedicated on specific sectors such as medical, food, construction products, and others. And individual CABs, which are the individual laboratories, inspection, certification, notified bodies that will have the possibility to join directly the organization. And last but not least, the international affiliates that will be organization worldwide. With this being said, our next steps are for the implementation of the legal aspects, and we will have as a target timeline to end the implementation and to set up all the practicalities to restart with the new categories of members at the end of this year. Thank you very much. In case you have specific questions, please drop me an email at my email address, which is here on the screen. We are happy to answer to any of your questions. And now, because of the time shortage, I would like to give the floor to our next speaker for the welcoming remarks and some few words on Eurachem to Eugenia Totu, who is the current chair of Eurachem, and she will provide you also very few introduction remarks, and then we will go to the topics dedicated for our webinar today. Eugenia, please, the floor is yours.
Okay, thank you very much, Laura. Welcome to everybody to our webinar. As Laura mentioned, there is a sort of time shortage already, so I will try to keep it as short as would be possible. The short presentation of Eurachem as organization. So could you see my screen? Yeah?
Yes, very well.
Okay, thank you. So, as you know, the main topic of today is dedicated to the guide, validate measurement procedures that include VaMPIS. And we hope that you'll be able to explore together with our experts and the authors of this guide, how to ensure the validity of your measurement. Now, very briefly, very shortly, I would like to present you what Eurachem is, being an European network which was founded back in 1989 and comprising 36 European members, full members, and associated memberships. And the main focus of Eurachem as organization is on the analytical quality through the traceability of measurement results, method validation, measurement uncertainty. And also important to be underlined is that Eurachem is providing guidance document and also is organizing workshops and training events. And as Laura mentioned, we also have important cooperations with European organizations and also international organizations. And the main activities that Eurachem is developing, as already mentioned, are the workshops and training, and lately successful webinars, as we hope that this webinar of today will be, the guidance documents, and also some supplementary documents that would support our guidance document, the guides that are provided by our working groups, and also a significant number of leaflets, which are intending to underline important issues presented in our guidance documents. These guidance documents are freely accessible through our website, eurachem.org, and you could access them, some of them also in your own language, because the translations are possible by our Eurachem members. Our currently active working groups are education and training, measurement uncertainty and traceability, method validation, proficiency testing, qualitative analysis, as well as reference material, and the working group uncertainty from sampling, which is directly involved today in the organization and is supporting this webinar. Then analytical equipment and system qualification, and we have some joint working groups as EEE proficiency testing, and the last one that we established together with EUROLAB on the digital transformation. Now, focusing a little bit on the activity of the sampling uncertainty working group, which is developing, the main aim of this working group being to develop comprehensive evaluating and combining uncertainties arising from the sample preparation specifically, formed a joint task group together with Eurachem method validation group and EUROLAB and, of course, NMKL, aiming to develop this guidance on the validation of the measurement procedure that include sampling, shortly known as VaMPIS. This trying to focus on balancing quantitative versus descriptive methods, as well integrated versus isolated validation procedures. And I hope that this webinar today would clarify some of your questions if you would have any. We developed, we are saying, a quite nice poster for our guidance, for VaMPIS guidance, and on the bottom are the QR codes through which could be accessed the guide. As I already mentioned, Eurachem is organizing a significant number of workshops face-to-face. We reverted to face-to-face meeting. Our last two workshops took place, one in Nicosia in the last March, and the workshop was dedicated to ISO 17025 and ISO 15189. And the very last workshop was held in Bucharest at the end of May on the complex matrices applications laboratory and accreditation. And our last webinar, which was, we are saying, a quite successful webinar, was dedicated to the reference material for the qualitative analysis and was organized in the last September 2024. Regarding our administration between 2024-2026, the Secretariat is assured by the Association Eurachem Romania, and I am the actual chair of Eurachem, and the next chair, the actual vice chair, is Helen Cantwell, and the past chair is assured by Isabel Verkris from Belgium. You could follow our activity through our social media channels, through our YouTube channel, and you could also access our LinkedIn page, and also the latest news from us. You could find them through our Eurachem blog, e-news, and our newsletter. And taking this opportunity, I would launch the kind invitation to you to subscribe to our news mailing list, which is accessible through our website. We had our last General Assembly at the end of the last month, 29-30th of May in Bucharest, Romania, where we were very happy to meet face-to-face, all of us, and to state again that Eurachem is people, that we are feeling that we are a family. And before closing this extremely brief presentation of Eurachem, I would kindly draw your attention to the fact that at the end of the present webinar, we'll be launch a feedback form and attendance certificate request. This could be accessed either through the QR code, either through the address eurachem.org/VaMPIS 2025. Both of them will be provided to you in the chat. So this being said, I hope that I complied with only 5 minutes that I was planned to present to you some of our Eurachem highlights. Thank you very much, and let's begin. So I think that Marius or Laura, you could take over and start properly our webinar for today. Thank you, and let's have success for today.
Thank you very much. Thank you very much, Eugenia, for the kind introduction. Now I have the pleasure to hand over the floor to Marius Kostaskis, and he will be our moderator for today. He is an assistant professor of analytical chemistry at the Department of Chemistry of the National University of Athens. And since 2019, he has also been a member of the Eurachem Method Validation Working Group and the Joint Task Force on Validation of Measurement Procedures that includes sampling. Marius, I will give you the floor. I wish everyone a fruitful webinar. And as I mentioned in the beginning, in case you have any questions during the presentations, please address them in the chat box. Marius, the floor is yours. Thank you very much.
Thank you, Laura. Good morning for all. Today we will start to have some presentations about the VaMPIS. So let's start quick with the first speaker. Our first speaker is Fernando. Dr. Fernando Cordeiro Raposo is retired from the Director General Joint Research Center with the European Commission, where he conducted research on environmental food safety and food quality. Previously, he held roles as an internal auditor for 17025 and 17043 as a consultant and position in both pharmaceutical products, laboratories, and quality control. He's a member of joint Eurachem working group on uncertainty from sampling, and of course, editor from the VaMPIS guide. So, Fernando, the floor is yours. The speak of Fernando is about the need for VaMPIS, a regulatory point of view. So, Fernando, the floor is yours.
Good morning to everybody. Can you listen to me?
Yes, very clear.
Okay. Just I have to.
Please make a full screen.
Yes, that's it. So, yeah. Now, is it okay?
Yes.
So, good morning again. Sorry for this. I could not see the option for a presentation. So, this is a relatively small presentation to explain you why we need VaMPIS, validation of measurement procedures, including sampling, from a regulatory point of view, or from, let's say, from accreditation, when the laboratories need to justify their accreditation. So, wait. Why this is not? I have a problem.
Yes. Press the next.
Yeah, that's it. I'm trying. I did this so many times, and today is not.
Have you tried pressing the up and down buttons?
Yes.
And the
Up
left
and
and right?
down. Yeah, nothing works. Oh, yeah.
Or left, right arrows.
Yeah, that's what was always okay. If you don't mind, okay, wait a second. I'm going to do it again.
Please press again to check.
And no, I apologize.
Would you like to go outside the full screen and do it again?
Oh my God.
Maybe if you just did it in normal mode and not in presentation mode, that might be easier.
Okay.
Change the first slide and put them in the first.
Yeah. I have a. It doesn't work. I apologize. Laura, can you put?
Click from here. I think it should be fine.
Can you put the slides and it doesn't work, and I tried so many times.
Oh, okay.
In fact, I can skip the animation. Is not important, but I'm trying for the last time. I will try it. Okay.
Yes.
Now I have here diaporama. No, it doesn't pass to full screen.
You can also just do it like this.
Yes.
Can I do it like this?
Yes. So you can just click through. It doesn't have to be in presentation mode.
Okay. Well, I really apologize. Well, but you see, it's not very nice. But well, so I start. I apologize for this waste of time, but my presentation lately is very small. So I hope you agree. We all agree that most, sometimes even all, laboratory activities nowadays, testing or calibration. My personal experience is more or less in testing anyway, but are carried out under accreditation. So ISO 17025 And other dedicated standards, I include this one because, in fact, the 17025 is the general requirements for the competence of testing and calibration in laboratories, but in a particular application, they may other international standards may apply. So it depends. So it means that under accreditation, if a laboratory has to justify their testing capabilities under accreditation, they need to demonstrate wherever they follow a particular measurement procedure, their results are accurate, adequate precision, trueness, and plus all the other performance characteristics that you know. I'm not listing them. I will put the Eurachem guide dedicated to that, but you know LLD, LLQ, sensitivity, linearity, and so on and so on. So how to achieve this? Very important. So it's a well-managed quality system. So all laboratories should have competent people dedicating most of their time to a quality system. So it means that they have some important documents like the quality manual, procedures, working instructions, and what is more dedicated to the presentation of today, validation reports. So our laboratory can design, in fact, laboratory manager, quality team, I should say. Normally, it's not one single person who does this. So how to design the validation of a measurement procedure. So of course, there are support, there are guidelines. The fitness for purpose of analytical methods is a guide from Eurachem, which has very recently republished, so reviewed and republished in 2025. And of course, one of the supplements that has been produced always by the Eurachem Working Group on Method Validation is the Planning and Reporting Method Validation Studies. And both of these documents, they recommend strongly using test samples, so routine test samples, real samples. Spike the sample, so you can spike a routine test sample to a level of a contaminant that is desired for. And of course, certified reference materials. Ideally, matrix match to the test samples that you intend to use the measurement procedure. So certified reference materials are often, almost, regarded as ideal for assessing simultaneously the precision and trueness because they have a certified value. However, and that's what I want to a little detail, if you use, and this was done even by in my past activity in the Joint Research Center, we were designing the collaborative trials using certified reference materials for assessing precision and trueness. But what people try to forget that certified reference materials are also sampled. They have been sampled. However, the certified reference material producer has to comply with the ISO 13034, which is the ISO dedicated to provide the requirements for certified reference material producers. And in particular, what concerns what I want to talk, the ISO Guide 35, which is dedicated to how to demonstrate adequate homogeneity and stability of certified reference materials, which means that the certified reference materials are processed and, if necessary, reprocessed to achieve an adequate homogeneity. I'm not presenting to you, there is a very easy equation that explains this requirement extremely easy, but I'm not presenting to you. We just say that any measurement procedure, of course, they have the sample preparation, but these steps in usual routine methods are quite less demanding than what a CRM producer has to do to the same, could be the same material to produce a certified reference material, which means that this leads to what? Leads that if you assess the intermediate precision of a measurement procedure using exclusively or mainly certified reference materials, even though the certified reference materials have been sampled, as I said, different test portions taken from a CRM unit or different units on different days will show lower variability for sure than test portions from test samples. means that this leads to that the lower heterogeneity of the certified reference materials, the intermediate precision using exclusively certified reference materials are expected to be better than using routine test samples. So just to remind you that this may happen, and in fact it happens. So how about sampling? So the ISO 17025, there is a section dedicated to sampling, and it requires, so it's a requirement from this international standard, to have a sampling plan and a sampling method. And after there are many, I just select two statements which are in this ISO 17025, could be selected different ones, but the sampling method shall address the factors to be controlled to ensure the validity of subsequent testing or calibration. So very important. So you have to address, try to identify which are the factors which may affect the reliability of the results that you do it using these samples. And sampling plans shall be based on appropriate statistical method. This I won't comment. You will see later on the presentations of today. So, in fact, you are not left alone. You have the, again, Eurachem is working for producing guidelines to help testing laboratories to achieve a certain level of competence. And as you know, there is a measurement of certainty arising from sampling, a guide to method-based approach, which was published in 2019. And of course, the one that is presented today, validation of measurement procedures that includes sampling. So you have available guidelines to work on it. Which means that wherever a lab manager, a quality manager, and I should say, as I like to say, a quality team in any testing lab, they have the duty to review the sampling plan and the sampling method. No matter if this is the sampling plan and sampling method has been designed in-house by the testing lab themselves or by an external sampling provider. So this is a requirement for the ISO 17025. Ultimately, the laboratory manager should be considered responsible for the effects of sampling on the measurement result. So it means that due to the known or expected variability within each sampling target, a composite sample, abbreviated to CS, composed by n samples increments, it's called increments, but in fact is individual test portions or individual samples, seems quite appropriate. And which means that, for the most important, wherever the conformity is to be assessed, one single sample, so one single increment would be lacking some representativity. I hope people agree with me. The duplicate design, and this is the most simple duplicate design that you can imagine of. You will see later today the duplicate design presented in the VaMPIS is far more complex because they have different sampling targets and more composite samples. But at least this is the one that I considered minimum to ensure that the mean of these four results, so two composite samples, two test portions from each composite sample. So it means that each composite sample is analyzed in duplicate. This would be minimum for, in my opinion, to have a result which could be eventually, if agreed by external requirement or by a customer or by even a legislative purpose, could be used for a conformity assessment. So, continuing with conformity assessment, regulatory bodies, normally they use all available information when setting the legal limits, example, a maximum limit for food contaminant, and also for target uncertainty, abbreviated to TU. Where do they can get this information? One that I did it for several years, the Joint Research Center was organizing proficiency tests organized by the acting as European Union reference laboratory. These laboratories are nominated by European Commission. I'm speaking within the European Union, of course. At the time I wrote these slides, so it means 1 week ago, I found that there are actually, presently, there are 46 European Union reference laboratories, each one dedicated to a particular analytical application. Imagine the European Union reference laboratory for some selected pesticides and some selected food and feed matrices. This is one example. We have done for food contact materials and for many others. Which means that each member state, there's also to nominate the most proficient testing lab in each particular analytical field, which is named National Reference Laboratory. And in addition, within each member state, there is also the other laboratories who also are officially controlling this, which are named official control labs. What I want to say is that wherever the European Union Reference Laboratory, which under their mandate, they have to organize at least 2 proficiency tests for this purpose, it can, and we have done it, we can organize the proficiency test for a particular case. And if the national reference laboratories demonstrate an adequate consistency among them, it is possible to use this as an excellent information tool to help regulatory bodies to decide, well, if there is enough consistent for this application, we can eventually suggest lowering, for instance, lowering the legal limit so this type of information is very important. The other way is the validation reports of new methods, improved methods, for instance, extended scope. So sometimes you may be trying to add one other food commodity to a method that exists already. So this is also very important information for deciding, is the method capable to measure at a certain level? So legal limit can be done or not at this level. Any other publications providing evidence for a capability of measurement at the or close to a certain legal limit, with all the performance characteristics of measurement procedures demonstrated, is also a very good source of information for regulatory bodies to set conformity legal limits. For target uncertainty, I won't talk too much about this, but there is a very good Eurachem guide published in 2015 dedicated to setting and using target uncertainty mechanical measurement, which provides many different ways how to set the target uncertainty. And now, my last slide, why do we need VaMPIS? Well, sampling. Once sampling has been recognized as being part of a measurement procedure, it shall be included in the overall validation. It means that should not be ignored. Sampling plans and sample methods, either designed in-house or by an external provider, shall ensure the validity of testing. So this is the responsibility of a lab manager, quality manager, and why not? We can envisage this as a co-responsibility with the sampling provider. If the sampling provider is a competent and external organization to the testing lab, but should participate because sometimes they know more than the testing lab about the sampling targets where they go. Accreditation regulatory bodies, laboratory manager, quality team must be aware that the sampling component of their overall measurement certainty shall not be ignored. And to do this, well, that's why we are today here. We provide guidance documents. We provide these sort of webinars to try to clarify these issues and try to help. And we are here to help. So today we will learn as well from your comments and your questions. And from my side, that's all. Thank you very much.
Thank you, Fernando, for the brief presentation about the sampling and in regulatory point of view. We have a short of time, so I would say every participant that have any question, please write the chat box, and then at the last session for questions and answers, we will have time in order to Fernando answer your questions. So let's go to our next presentation. The next presentation is a joint presentation by me and by Mike Ramsey. So Dr. Mike Ramsey is an emeritus professor at the University of Sussex. Previously, he lectured in analytical geochemistry at the Imperial College for 20 years. He is a co-chair of the Eurachem Joint Task Group of VaMPIS and co-editor on published guidance of uncertainty of sampling and, of course, the VaMPIS. So together we are co-chairs in this joint task group. So our presentation is divided in two parts. In our first part, I will present you a little bit an introduction about the validation and especially for the terms and the different points of the uncertainty. Please tell me if it is in full screen, the presentation. Someone please confirm me that. Can you see the full screen presentation?
Yeah, we can.
Thank you. So our presentation is about the general approach to the VaMPIS validation of measurement procedure that includes sampling. So an overview about our presentation. My first part will be about what is validation. We will make a reminder, of course, about the sampling component of validation, the criteria of validation, and the second part of Mike Ramsey will be about the approach of VaMPIS, the flowchart, the key role of the measurement uncertainty, and the application. So let's start. A few words about the validation. Already in the last edition of ISO 17025, verification is the provision that the evidence of that given fulfills specified requirements. And of course, validation is the verification where the specified requirements are adequate for an intended use. So when we speak about method validation, in reality, we're speaking for all the parts of the measurement, from sampling until to analysis. On the other hand, in the most of the case, laboratory choose to exclude the primary sampling of the component, and the most of the validation are taking place only in the activities within the walls of the laboratory. Are all the procedures of sampling excluded? Of course, in many cases is not. There are some ways that we have a gray zone that we are validate our method, included the subsampling. So let's say the sample handling in many methods take place in the laboratory, but again is always within the walls of a laboratory. So in the most of the case, the validation means something that take place only for the analysis component. On the other hand, in the last edition of ISO 17025, sampling is recognized as a part of measurement process. So in the paragraph 7.6.1, laboratories shall identify the contribution to measurement uncertainty. When evaluating measurement uncertainty, all contributions that are significant, including those rising from sampling, shall be taken into account using appropriate method for analysis. So if sampling is important, should be included in the method uncertainty, of course, and the validation part. When we are speaking about validation, we're speaking about the requirements. Requirements means performance characteristics. In analysis, we know very well those performance characteristics. Eurachem has already a guideline almost 30 years for the fitness for purpose of analytical method and propose the following performance characteristics that are already known: selectivity, limit of detection, working range, analytical sensitivity, trueness, precision, and ruggedness. It's something very well-known procedure, but in every case, they exclude the primary sampling. Because some primary sampling is difficult to assess, and especially with the same performance characteristics for sampling, it needs a lot of data that are necessary and also increase a lot of the cost in order to validate a method, let's say, according to the analytical component specification. For this reason, the new guideline about the validation of measurement procedures that include sampling published from Eurachem as a first attempt to include the sampling part. the key role in that guideline is the uncertainty. Uncertainty is not always recognized as a performance characteristic. On the other hand, also, additionally, uncertainty in analytical component of measurement is something very well known. It is calculated through the experiments that contributed the analytical uncertainty, bias, trueness, LOD, LOQ, and selectivity. There are many ways to assess those components and estimate uncertainty. We have data. We can assess that data through the proficiency test, Horvitz equation, target uncertainty, and of course, 35 years now, there are a lot of long-term data in order to evaluate and understand very well how they contribute the uncertainty of analysis. On the other hand, uncertainty in sampling components is, let's say, we have less data. There are two main approaches in order to estimate the uncertainty, the empirical one, top-down, and modeling, the bottom-up. In empirical one, there are two ways through the duplicate methods that most commonly used in the laboratories that do the uncertainty of sampling. And of course, sampling proficiency tests are being developed, have been increased last years, but currently most of them are in water and soil, have not become attempts in other matrices, but are increasing. So in the next years, maybe we have more data about them. Both, of course, assess the effects of the uncertainty sampling, so heterogeneity, degree of representative, and sampling techniques. In the empirical way, is the most reliable and most used. The modeling approach, in many cases, underestimates the data because it needs do a lot of simplification. But again, we have a few words with short-term data for sampling. So uncertainty arising from sampling analytical components can be, of course, estimated through the experimental empirical way, and is the key role for the validation. Here we have, let's say, the traditional way of uncertainty, the methodological approach that uncertainty is properly for the results arising only for the results. So it's a property for the result, not a performance characteristics. For this reason, some guidelines didn't include invalidation approach uncertainty in analysis. Of course, in our VaMPIS guide, the new integrated approach, the uncertainty is the key. Has the key role in order to evaluate and judge the fitness for purpose. In a webinar that take place on May 2022, 43% of the participants agreed that the integrated approach is, let's say, the most available approach for uncertainty. So this is that VaMPIS starts and applied in two main types of applications. Depends on the method that the laboratory used. The sequential way that one laboratory separate the analysis and sampling, and the simultaneous. Here I will give the speech to Mike in order to continue the next part of our presentation.
Good morning, everyone. My name is Mike Ramsey. I'm the first co-editor of the VaMPIS guide, and I'm going to talk you through the outlines of VaMPIS in this talk. Before we get down to the details, can everyone see my screen?
Yes, Mike. It's fine.
Okay. So here we have validation of measurement procedures that include sampling, VaMPIS. And we're going to use uncertainty of the final measurement result to judge its fitness for purpose. Is that measurement result going to be good enough to make the decision? And hence the fitness for purpose of the whole measurement procedure. So there is the VaMPIS guide, the front cover, and here is a QR code where you can download the I'm just trying to get the laser pointer. so I can point things out. Right, so we can apply VaMPIS either in two modes sequentially, which means when you've got an analytical procedure that's already been validated and you're just adding the sampling to it, or you can apply VaMPIS simultaneously. You can take the whole measurement procedure and validate it at once, sampling analysis together. You can apply it to ex situ measurement procedures, and that's the traditional system where we take a sample in the field and we bring it into the lab, as you can see on this diagram here, the field and into the lab. Or we can apply it also to in situ measurement procedures. Increasing number of measurements are made without the physical extraction of a sample. We just place the sensor down, so we can validate that with this approach of VaMPIS. This is the flow chart of VaMPIS. It may look a bit intimidating to start with. It's got 11 steps, and I'm going to talk you through some of the key steps. 5 I'm going to talk about in this talk, and we'll go through more of the others in later talks with examples. So specifying the measurand and the sampling target, the key thing. Identifying the measurement procedure, that's the sampling procedure and the analytical procedure. Estimating the measurement uncertainty, and then deciding whether that is the measurement uncertainty is good enough. Is it fit for purpose by comparing it against a target? And then we might need to modify the measurement procedure to achieve fitness for purpose. So let's start with the specifying the measurand. The measurand, the quantity intended to be measured is its definition. So it might be the average nitrate concentration, for example, in lettuce, and we'll talk about that. Or it might be the average lead concentration, for example, in soil to a particular dry basis, say. And then we've got to identify and specify the sampling target. That's the portion of material at a particular time that the sample is intended to represent. So it could be a whole batch here of lettuce growing in a greenhouse, say 20,000 heads in a batch, and we're going to use that in one of the examples. Or it could be an area of land, and here, say it's a 30 by 30 area of soil that we're trying to characterize. So we want to identify the measurement procedure. So that's the sampling procedure and the analytical procedure with those abbreviated forms. Typically, they're already documented somewhere. And as I've said, the analytical procedure might already be validated, in which case we apply the sequential approach. But if not, we have to use the simultaneous approach where we validate the whole measurement procedure. And we can apply this, as I've just said, we could apply it to these in situ measurements. For example, portable X-ray fluorescence. And I'm going to give you an example of that. When we want to estimate the measurement uncertainty, as Marios has just said, we could use something like the duplicate method. And I'm going to talk you through that, where we have a sampling procedure here where we take 10 heads of lettuce where the little green dots are to represent the 20,000 lettuces in the batch. But that W design that's specified could easily, just as easily, have been applied the other way around. What effect would that have on the measurement value? What is the uncertainty that's arising from sampling? And that's to do that, we've got to do this duplicate design and then separate out the different components of the uncertainty, that arising from sampling and that arising from analysis, using this statistical technique called analysis of variance. And I'll talk you a little bit through that in the later talks. If you've already got an estimate of the measurement uncertainty arising from analysis that the lab has internally, you tend to use the larger value. If the duplicate method gives a larger value than the lab thinks, then it's probably the duplicate method is probably more realistic. And I'll talk about that a bit later as well. The judging for fitness for purpose, we compare it, the actual measurement uncertainty against a target. But the target has to include, the target measurement uncertainty has to include uncertainty from sampling, and they don't always do that. Ideally, it'll be set by a regulator or a customer. But if none is set, you can calculate a target measurement uncertainty. And one way of doing that is with this optimized uncertainty approach. And in later talks, we'll talk about this special software, Optimu, which is available from an AMC website where you can do these calculations. If the actual measurement uncertainty, including sampling, is around the target value, then we can judge it as fit for purpose. But if it's substantially, say, above the target uncertainty, then it's not fit for purpose, and you have to go to the next step, step 10, to modify the measurement procedure. But you have to then decide whether to improve the sampling procedure or the analytical procedure or both. And we'll talk about how you can do that. There's output from this Optimu software that helps you identify which is more cost effective, improve the sampling or improve the analysis. If you need to reduce the uncertainty from sampling, you can increase the number of sample increments is one way of doing that, and we'll talk about that. If the uncertainty from an analysis needs reduction, then you can review the 7 performance characteristics that Marios talked about, that the traditional characteristics of an analytical method, as a way of reducing that component of the measurement uncertainty. So we're going to do worked examples. The first one, example A1, nitrate in lettuce, ex situ measurement with the sequential approach, because the analytical method is already validated. We're going to talk about the estimation of measurement uncertainty from sampling. I'm going to do that in the next talk. And then Peter Rostron is going to talk about judging the fitness for purpose in that example by comparing against the target uncertainty and how you calculate that. Then Peter's going to talk about the second example in the VaMPIS guide, lead in soil with an in situ measurement device, the PXRF, and that is the simultaneous approach where you validate the whole measurement procedure, all the components, all in one process. So the conclusions, the general approach of VaMPIS builds on the existing approach for validating analytical procedures. We always base it on quantitative demonstration of fitness for purpose rather than anything descriptive. The VaMPIS guide, and here's the QR code again, we're going to validate the whole measurement procedure and increases the role of measurement uncertainty as it reflects all the components of the measurement procedure, including the sampling and the physical sample preparation, which we sometimes forget. What happens between the field and the lab? Is it in a van? Is it deteriorating? All these issues, is it kept at the right temperature? That would all affect the measurement uncertainty. And then we're going to look at these practical applications of VaMPIS with worked examples. So whether we have time for questions now, I'll leave to Marios. Marios.
Yes, thank you, Mike, again for this description about the VaMPIS approaches. So far, we have one question for Safa about the sampling of food contact materials and how we can deal with. I think because it's an application example, maybe we can leave for a question after your descriptions. If you would like to discuss about that, we have 1-2 minutes before continue. But because it's an application question, I would like to maybe leave it for the next after discuss the examples, after we have a practical description. You agree, or you would like to?
Yeah, I can agree. So should I finish this presentation and get on with the next one? Yeah.
Yes. So the next presentation of Mike Ramsey is about, we start now a section about the application of VaMPIS So the first presentation is estimation of measurement uncertainty, including sampling, and we have here some application examples. So Mike, please.
Okay, let me just load up my presentation. Right. Let me see if I can just, if you could bear with me a second, I'm just going to share. Right. I'm going to right. Can you see my presentation, everyone?
Yes. Yes.
Yeah?
Yes, Mike.
Okay.
It's fine.
Right. So I'm going to go to the first example now of the application of VaMPIS. So this is an ex situ determination of nitrate in lettuce, in glasshouse lettuce. And I'm going to focus this first presentation on the estimation of measurement uncertainty from sampling. And then Peter will do the second half of the application of VaMPIS in the next talk. So the overview, the need for measurement uncertainty estimation within VaMPIS, a little bit on what is measurement uncertainty, just to make sure we all agree on and explain a little bit, and that it needs to include contributions from all parts, including the sampling. And uncertainty from sampling, I'm shortening here as being this abbreviation UFS. A little bit reiteration of the role of 17025 in saying that measurement uncertainty should include this uncertainty from sampling. A little bit on how we're going to express measurement uncertainty, and then how we're going to estimate it in this step of the VaMPIS process with the duplicate method. With this example of nitrate in lettuce with the ex situ measurements in the lab, and then lead on to Peter's talk. So I think we've had a little bit of discussion already about how measurement uncertainty is the primary performance characteristic for judging fitness for purpose for this whole measurement procedure. And that is because it's the only characteristic that unifies the effects of all the steps, including not just the sampling, but as I've just said, the physical sample preparation, whether it happens in the lab or in the field or between the two in transport. It reflects all the 7 other methods performance characteristics, but with the addition of sampling. And as Fernando pointed out, measurement uncertainty is used in compliance decisions. It's the only quality issue metric that gets right through to that stage. So we're going to go on to this estimation of measurement uncertainty, including uncertainty from sampling, this step in the flowchart using ANOVA. So this measurement uncertainty, I'm going to use this historic definition here, where measurement uncertainty is an estimate attached to a test result. So here's our test result. This is interesting. Yes, that characterizes the range of values within which the true value is asserted to lie. So in this older historic definition, we've got this concept that there's a true value here. We don't know where it is. It could be anywhere between this lower confidence limit and the upper confidence limit. So what we need to know is this uncertainty value, so we can at least say the range within which the true value lies. And of course, in the later definitions from the GUM and the VIM, the true value is replaced by the value of the measurand. But that is the quantity intended to be measured, which is pretty much equivalent to the true value. And it's obviously going to include the random effects and the systematic effects from things like trueness and quantified as bias. And it's going to have contributions from all the steps in the measurement procedure. So as has already been pointed out, it's in ISO 17025. I won't read it again, but there's the section 761 that Marios mentioned, saying that sampling should be taken into account in estimating measurement uncertainty. And it's also in 763, laboratories performing testing shall evaluate measurement uncertainty. And the ILAC accreditation committee decided that this section is also valid for sampling, that should be included. So it's pretty unambiguous now that it should be included. I need to have a statistical model if we're going to do this estimation of measurement uncertainty using the empirical approach that was mentioned by Marios. Don't be daunted by the equations. This is just when we have one sampling target, we'd really like to know the true value of the analyte concentration, but all we have is this measured value, little x. The difference between the two are the effects of the analysis and the effects of the sampling, and that's what the equation says. If we look at the standard deviations of these components and we square them, we get something called the variance. And the variance that come from these last two components, the sampling and the analysis together, we're calling that the measurement variance. Hence, we're getting the measurement uncertainty. The sampling is between samples on one sampling target, and a lot of that is due to analyte heterogeneity, but it's also due to the sampling technique. And then the analytical variance is the variance within one sample, and we often estimate that as reproducibility. Yes. And we don't have the true value of the variances. We only have estimates, so we use S instead of sigma. We often need multiple sampling targets in the duplicate method to have a number of sampling targets so we can get a typical value of what the heterogeneity effect is on this measurement uncertainty. When we have multiple sampling targets, typically something 8 or more, this same equation here, we have one extra term, and that's the variation between the different targets. So the measurement, the value of the variance of the measurements is just the same, sampling plus analysis, as we had in the last slide. But now we have this extra term between target variance. And using our estimates down here, the total variance has got these 3 different components. And it's only these last 2 components that give us the variance of the measurements. And our standard uncertainty is the standard deviation of the measurement. So quick recap, I'm sure you've all expressed measurement uncertainty, but just to give an overview and see how it fits in. The standard uncertainty, little u, is often just the standard deviation of the analysis, but it really should be the standard deviation of the measurement, as we've just said, including sampling. The expanded uncertainty we multiply by a coverage factor, typically 2 for 95% confidence, this K value here, the coverage factor. But if we have only a small number of samples, then the K probably needs to go above 2. And there's a paper in Aqual here where we go into that in more detail, and there's some new software, Ranova 4, on the AMC website that allows you to calculate these K values when you've got small numbers of samples. The expanded relative uncertainty, we divide through by the concentration and multiply by 100. But we can also express the measurement uncertainty just as with the confidence limits, lower and upper. And if the uncertainty is high, over say 20% relative, then you might need the uncertainty factor. Or if the distribution is log normal. I don't have time to go into that, but I can give details for people who need it. So let's now look at the duplicate method. So in this, what's called the balanced design, where we have a sampling target, selected sampling targets, say 10% of all the targets, from that one target, we take not just one sample, but we take a second sample by reinterpretation of the sampling protocol that's equally likely, and we'll show this in the example. And for each sample, we take duplicate analyses, 2 on the first sample, 2 on the second. So the sampling target may be the bay of lettuce, the area of land, whatever, and the duplicate samples give us variation within each sampling target caused by the sampling uncertainty. But the analytical repetition here gives us, in this design, repeatability, precision. The advantage of the duplicate method, one advantage is that you only need one sampler to do it, but that means you don't get between sampler bias. If you want to include between sampler bias, and it can be important in sometimes, you need a more sophisticated design like sampling proficiency testing, collaborative trials in sampling, and that's described in the VaMPIS guide. And I'm going to explain this duplicate method with a case study, and it's going to be applied both to ex situ and in situ measurement methods where no physical sample is withdrawn, and Peter's going to talk about that. So let's talk about the flow chart, the first 3 steps for this case study with the nitrate in lettuce. So the specification of the measurand. Well, the measurand in this case is the nitrate concentration, and the sampling target is the bay of lettuces from, say, 12 to 20,000 heads. And there's a threshold value for nitrate in lettuce of 4,500 milligrams a kilogram as the limit for human consumption, which we're going to obviously try and make decisions on. Identifying the measurement procedures. Well, the sampling procedure is specified in this EU directive down here, and it specifies taking 10 heads or increments to make a composite sample for each sampling target. The analytical procedure is all, as I mentioned, already validated. The HPLC method was a collaborative trial between labs was used, and the uncertainty from analysis was characterized at around 6%, based on a RSD reproducibility of 3%. But now, of course, we need to extend this out to the whole measurement procedure, including the sampling and the sample preparation. And we're going to use this measurement uncertainty to reflect the performance of all the 7 normal performance characteristics on the analytical side, plus the sampling. And then we can judge its fitness for purpose by using the actual against the target uncertainty, and that's what Peter's going to do in the following talk. So the estimation of measurement uncertainty, we don't just use one sampling target, we need to take a range of sampling targets chosen at random, so they give us a view of what the heterogeneity of their nitrate might be typically across these batches. And each of these sampling targets, we don't just take the first W design, 10 heads for sampling 1, we take the second to give us an idea of what the effect might be of orientating the sampling pattern a different way. So there we had the W design with the 10 heads, as I showed you before, one way around, and then of the 20,000 heads. And then we apply the W the other way around, because they're both equally likely interpretations of that design. And these are the measurement values for the 8 sampling targets for the balanced design. So here's sampling 1, analysis 1, analysis 2, sample 2, analysis 1, analysis 2. And you can see here that the analytical duplicates agree pretty well. The sample duplicates don't agree as well, because obviously we've got these sampling uncertainty components coming in. We've got a good range of variability between the different batches. We can see those differences, which is good. But is the uncertainty in the analysis and the sampling fit for purpose? Can we still make decisions? Can we, for example, decide, I'm trying to, can we make reliable decisions as to whether these batches are over or under the threshold value? Is batch G under, is batch D over the threshold value? And it's the fitness of purpose that's going to tell us that. So to do that, we've got to estimate the measurement uncertainty and separate out the components. And we do this with this analysis of variance. There are a number of packages for doing this, but there's a free one, RANOVA 3, that's available using this QR code. It comes from the Royal Society of Chemistry Analytical Methods Committee. It can do classical ANOVA that assumes a normal distribution. But in this particular case, if we take those measurements I've just shown you and put them into a histogram, we can see it isn't quite a normal distribution. It's got some outliers here. And we need to use something called robust ANOVA, and that can accommodate up to 10% of outlying values and give a robust estimate of the uncertainties. So this is the output of RANOVA 3. There's classical ANOVA here and robust ANOVA there. But we're going to ignore the classical ANOVA because we've just seen it's not a normal distribution. We need to focus on the robust ANOVA here. And we've got these different components of the variances that I showed you on the previous slide, the between target sampling and analysis. But it is these last two added together by sums of squares that gives you the measurement uncertainty here. The standard measurement uncertainty, 361 milligrams a kilogram. And if we want it as relative expanded uncertainty, it's 16% for k equals 2. Interestingly, if you just chose the analytical uncertainty, as often happens, we'd only get 7.6%. So we'd underestimate this 16%. So we'd severely compromise our compliance decisions. So those are the results I've just shown you, the 361 and the 16%. But even these don't include measurement uncertainty between days, operators and labs. But they are based on a test portion which is realistically heterogeneous. And Fernando mentioned that if you use a certified reference material, you tend to underestimate the precision because it hasn't got realistic heterogeneity. But this initial estimate hasn't got analytical bias included, but this can be estimated obviously from certified reference materials or spike recovery, and it can be added, and the uncertainty from sampling guide on page 50 shows you how to do that. In this particular example for nitrates in lettuce, the bias was not statistically significant, so it wasn't added in. There's also measurement uncertainty from sampling bias, but we didn't add this in this example. We need something like a sampling proficiency test with a number of organizations to do that, and there's a worked example of that in the paper that's shown there. So the limitations of the duplicate method. The ANOVA estimates the uncertainty from sampling, but the uncertainty from analysis just as repeatability. And if, as I mentioned earlier, if the internal lab's internally estimated uncertainty from analysis is larger, that should be used in place. But in this example, as often happens, the uncertainty that the lab attributes to this method was about 6%, where from the duplicate method is bigger, it's 7.6%. Even the fact that it's excluded a lot of the sort of between technique effects and between operator. So this time we'll use the uncertainty from the duplicate method, uncertainty from analysis from that source, because it's bigger. We now have to judge whether it's fit for purpose, and that's going to be what happens in the next talk. So I'm going to leave that for Peter to talk about. So my conclusions are sampling is part of the measurement process, so it needs to be included, hence invalidation, so hence VaMPIS. The measurement uncertainty needs to include the contributions from sampling, and measurement uncertainty is the best performance characteristic because it summarizes the effect of the 7 others method performance characteristics and also brings in uncertainty from sampling. And it's the only quality metric used in compliance decisions. We can estimate uncertainty, measurement uncertainty using the duplicate method at the validation stage, but it can also be monitored with ongoing quality control. And the final talk in this morning will elaborate that, how we can use it in quality control. And it enables us, the measurement uncertainty, to make more rigorous validation of the whole measurement procedure by comparing the actual against the target uncertainty that's going to be covered in the next talk. So thank you very much, and I'll leave it at that point. Thank you.
Thank you, Mike. We are approximately 5 minutes delayed, so we are okay about the time. So I would like to introduce the next speaker. The next speaker is Peter Rostron, focuses on estimation of measurement uncertainty, including the contribution for sampling, including the production of RANOVA software available for website of UK Royal Society of Chemistry, Analytical Method Committee. He is a member of Eurachem EUROLAB CTAC Nordest AMC working group, and he's also co-auditor of 2019 edition of Measurement Uncertainty Arising from Sampling, and of course from the VaMPIS guide. The first speak of Peter, and then we will have a break, is for judging fitness for purpose by comparing actual measurement uncertainty against the target measurement uncertainty. So, Peter, the floor is yours. I would like to remind you that you can write all your questions in chat for now, and in QA session we will have time for also discussion.
Good morning. I hope you can all hear me and see this presentation, which I'm trying to put into full screen mode and not having much luck with.
Yeah, so far it's not full screen, but we can see your presentation.
Yeah, I'm just trying to, sorry, I'm pressing F5 and it doesn't work, so I'll try the...
Here. Yes.
Ah, there we go. Right.
Great. It's fine.
Okay. So we are, I presume everybody can see that. We are running a little over, so without further ado, I will begin the presentation. So the last 2 presentations looked at the general VaMPIS approach, and the second one concentrated on step 7 of the VaMPIS procedure, the estimation of measurement uncertainty using the duplicate method. In this one, I will look at the subsequent steps, with particular emphasis on the calculation of a target measurement uncertainty when one is not specified by a regulator. So as a brief overview, I'll discuss judging for fitness for purpose by comparing the MU with a target uncertainty value. Then I'll describe a method called the optimized uncertainty approach, which has 2 parts. First, to calculate the optimized uncertainty, which can be used as a target uncertainty, and secondly, to apportion expenditure between sampling and analysis. I'll describe the inputs to the optimized uncertainty method, and finally show an example of its application. So how do we judge that the measurements are fit for purpose? Well, as Mike previously said, the overall measurement procedure, overall measurement uncertainty might be considered the one key metric that encompasses the uncertainties at every stage in the process, and that's from the initial acquisition of primary samples right through to the reporting. This can be compared to a target measurement uncertainty. The question is, where do we get the target uncertainty? So in many cases, this should be predefined by a regulatory body, including the uncertainty arising from sampling, but in situations where this is not the case, an alternative approach is needed. Several approaches are described in the Eurachem guide on setting TU, reference down here. Here we will look at an approach called the optimized uncertainty approach. So the optimized uncertainty approach balances the costs of making measurements with the potential probabilistically calculated costs of making incorrect decisions based on those measurements. But what do we mean by incorrect decisions? This could either be financial loss that arises because we have rejected a batch of material, we rejected a batch of material or condemned it in some way because, for example, the measured value is above a maximum regulatory threshold, whereas the true value is actually below it. And we'll call this a false positive scenario here. Alternatively, we might falsely accept a batch of material that is actually non-compliant. This might lead to costs such as legal costs and reputation costs, and this is a false negative scenario. Just to point out, consequence costs can only be estimated where the financial information is available and relevant. So the OU approach, how does it work? Well, it models a financial loss function against increasing uncertainty levels. I'll describe this a bit more shortly, but suffice to say the minimum of this U-shaped function occurs at the uncertainty value that results in the lowest expectation of financial loss. There are two separate stages. The first stage minimizes the loss function to obtain the optimal uncertainty, and this can be used as an approximation of a target uncertainty. The second stage is useful in the event that the actual measured uncertainty is sufficiently above or below the target uncertainty that we deem the measurement procedure not fit for purpose. So stage 2 of the OU method then enables an apportionment of expenditure between sampling and analysis that enables us to bring the uncertainty closer to the target. So looking at stage 1 in a little more detail, you see that we have increasing cost or expectation of loss on the vertical axis and increasing uncertainty on the horizontal axis. This is for a false positive scenario, which you'll remember is when we decide to condemn a batch of material unnecessarily. The grey line here represents the cost of those discarded or reassigned batches. The light blue line is the sum of the costs of both of those. It's the sum of the values of cost for both of those curves. And the OU method makes an assumption that cost of measurement will increase exponentially as you reduce the uncertainty. So here we have a hypothetical actual uncertainty at around about 350 milligrams per kilogram, but the optimal uncertainty has been calculated around 200. So the point is that although it may cost more in measurement to achieve the optimal uncertainty, in theory the actual expectation of loss is lower. So let's have a look at the inputs to the OU approach. First, and importantly, of course, we need a threshold value which will almost always be defined by a regulator and should include uncertainty from sampling. For example, the maximum lead concentration in dry soil or the maximum nitrate concentration in lettuce samples. It might also be a minimum, so for instance something like the meat content of sausages. Two measurement costs are required: costs of taking and handling each sample and the costs of analysing each sample, usually in the laboratory, but in some cases in the field, so for instance using a PXRF. Similarly, two uncertainty values are necessary: the uncertainty from sampling and the uncertainty from analysis. We've already seen how these may be estimated using the duplicate method. Next, we need the consequence costs of making a false decision. For example, the costs of discarding a batch and also a concentration value at which to optimise. This last parameter does require careful consideration and is discussed on the next slide. But note that while the previous parameters are generic to either false positive or false negative scenarios, these two are specific. Right, the CM parameter, the concentration at which the system is to be optimised, it requires careful consideration, as said. So it should be set to a value that could reasonably result in misclassification. It does not want to be too close to the threshold where we would assume that this would flag a concern in real life, but set to a realistic value that could reasonably be misinterpreted. Some previously used examples have been the median of non-compliant measurements, 10% above threshold for a false positive scenario, or a value such that the uncertainty due to analysis, when applied to itself, potentially results in misclassification. Right, so now we have the inputs to the method. How do we do the calculations? Well, the formula from Thompson and Fern are quite complex, although they have successfully been used in various spreadsheets. From this, the OU graph can be drawn and the optimal uncertainty simply read from the chart. But it's also possible to find the optimum uncertainty using a Newton-Raphson method. Again, you can do this on a spreadsheet, but it's fiddly and you'd probably have to change it for every experiment. So the new software Optimu, which is now downloadable free from the website of the British Royal Society of Chemistry, enables quick and easy production of the graphs for either or both false positive and false negative scenarios. It performs the stage 1 calculations automatically once correct inputs have been entered and finds the optimal uncertainty using the Newton-Raphson method. Stage 2 calculations are performed simultaneously, showing the factors by which the costs of sampling and the analysis for getting to the optimal uncertainty. It's automatically filled in once you've done the main calculation. So let's go back to the nitrate in lettuce example that was Mike introduced in the previous presentation, but as a brief recap, 10 heads of lettuce were taken from each bay to make a composite. Duplicate samples were taken by a reinterpretation of the sampling protocol, and the composite samples were analysed in lab by HPLC. So next step is step 8, which is judging whether the measurement procedure is fit for purpose, and we're going to assume that the target MU has not been predefined by a regulator, so we will use the optimized uncertainty method to decide a target uncertainty. So these are a breakdown of the inputs to the Optimu program. On the left you've got some general parameters for the displays, plus this is also where you specify whether there's a maximum or minimum threshold. So then we have a threshold value for nitrate concentration in lettuce at the time of the study was 4,500 milligrams per kilogram. The uncertainty value for sampling and analysis have been taken from the robust ANOVA. The consequence cost in this case for a false positive scenario was based on the rejection of a batch of lettuce heads. And finally, the concentration to optimize has been set to the maximum measured concentration that would indicate it is greater than the threshold when a compliant true value is measured, taking the analytical uncertainty into account. I'll show a bit more about this on the next slide. So in the Optimu program, next to the concentration to optimize field, there is a yellow help button, and if you press that you get this screen, providing you've got everything else filled in, that is. There are two automated options. The first one is, in this case, is simply 10% higher than the threshold, but we're actually using option 2. It is a value that could be a false positive reading when the analytical uncertainty is applied to CM, the concentration to optimize. To perform this calculation, Optimu needs to know the mean value of the analytical measurements, which is entered here. If you want to use another value, such as the median, you can just type it straight into the field. Right, so so now we've entered all the necessary inputs. Optimu has a big yellow button called Optimize, and the graphic and the optimal uncertainty will be calculated. So the next step in the VaMPIS process is to check whether the actual uncertainty is fit for purpose. So here's the optimization from the lettuce example. The actual and optimal uncertainties and their corresponding expectation of loss are shown at the top. The graph shows how the optimal uncertainty compares to the actual uncertainty. So in this case, the actual uncertainty appears to be too high and needs to be reduced by a factor of about 2 to be optimal. And we can say in this case that the measurement procedure as it stands is not fit for purpose. So we're suggesting that the optimal uncertainty can be considered a guideline target uncertainty for validation of the whole measurement procedure. So now that we have established that the measurement procedure is not fit for purpose, the next step in VaMPIS is to modify that procedure. This is where we use stage 2 of the OU method, and this part of the process has already been calculated by Optimu. At the top we have the optimal measurement uncertainty and the corresponding expectation of loss. Stage 2 subdivides the optimal measurement uncertainty into uncertainty from sampling and uncertainty from analysis, based on formulae from the original Thompson and Fern paper. This is intended to be a guide to what would be the most cost-effective way to get the actual measurement uncertainty closer to the optimal uncertainty. So in this case, the uncertainty from sampling can be reduced to optimal by increasing the sampling cost to €183. A more precise analytical method, which is assumed will be more expensive by the OU method, could also help to achieve that target uncertainty. But as the uncertainty from sampling accounts for 80% of the total MU, the best approach would be to reduce the sampling uncertainty. So, for example, based on sampling theory, taking a 40-head composite instead of a 10-head composite. And as a matter of fact, this was tried during the original experiment. The actual sampling reduction in sampling uncertainty was found to be a factor of 1.8, so close to the 2 that we'd expected. This would equate to a combined MU of 244 milligrams per kilogram, which is much closer to the optimal value. And also, of course, that means a substantial reduction in the expectation of loss. We should note on this slide, though, that this example is an approximation, because in this calculation we did not modify the cost per sample. Right, so the next step, the final step in VaMPIS, is to review the fitness for purpose of the analytical procedure. So the analytical uncertainty was previously estimated by a collaborative trial to be fit for purpose. The analytical uncertainty estimated using the duplicate method was found to be a bit higher, but not much higher. It might be surprising because the uncertainty from ANOVA did not include some of the variability present in a collaborative interlab trial, but an important factor is likely to be that it did include variability caused by heterogeneity in routing test materials. So now that is the test samples extracted from a macerated composite. So this being compared with using reference materials, which would usually have a very high degree of homogeneity. Anyway, the difference between these two uncertainties is barely statistically significant, even taking confidence intervals into account on the value from ANOVA, which we did using ANOVA 4. We don't have the confidence intervals for the collaborative trial. So we can conclude that the analytical method is still fit for purpose. So finally, using the OU approach suggests that the use of 10-head composite samples is not fit for purpose, and as we have seen, the sampling contribution to uncertainty means that a reduction in sampling uncertainty would be sufficient to achieve fitness for purpose without the need to reduce the analytical uncertainty. So in conclusion, in this presentation we have seen that fitness for purpose of an entire measurement procedure can be judged by comparing measurement uncertainty with a target uncertainty, where the target uncertainty includes the contribution from sampling. When a target uncertainty, including uncertainty from sampling, is not known in advance, it is possible to use the optimized uncertainty approach to calculate one. and where a measurement procedure is then found to be not fit for purpose, the OU approach also assists in apportionment of the two components of uncertainty, sampling or analytical, to bring the overall uncertainty closer to the target. Thank you. That is the end of my first presentation.
Thank you, Peter. Thank you. You are very good on time. We are exactly at the time for a break. If there is, of course, we continue. If there is any question, you can write the chat. And we have now a break of 15 minutes, so we will be again at 12:15 of Central Europe time. So then we continue again. After the break, we will continue with Peter again with the second presentation. So you have a nice coffee break, and if you have any question, of course, write down to the chat. So, Peter, you're here? Okay. Can you hear me?
Yes, you're audible.
So after the virtual coffee break, I hope to have a nice time. Let's continue with the second presentation of Peter about the application of VaMPIS in situ measurement example of lead in soils by XRF. So, Peter, the floor is yours. You can see now your presentation. And now,
okay. Everybody can hear me. So we're now going to look at an application of VaMPIS to in situ measurement lead in soil by PXRF. So the previous presentations gave an example of the sequential approach to VaMPIS, where the analytical procedure has previously been validated. This one looks at the simultaneous approach, where both the sampling and analytical procedures are validated as a single measurement procedure. It also provides an example of how the VaMPIS approach can be used for in situ measurements, in this case acquired using handheld PXRF on an area of land that was known to have lead contamination. Fitness for purpose was evaluated for two different purposes. Firstly, geochemical mapping, for instance, finding the spatial location of contaminated hotspots, and secondly, for comparison against a regulatory threshold. What are the advantages of using in situ devices? The results can be obtained relatively quickly in the field if needs be. They are relatively inexpensive to implement once you have a machine, that is. There is no or minimal sample handling involved, and the measurements can be made in field conditions. However, for instance in the case of PXRF, mathematical modelling shows that the mass of the test portion is very small compared to most laboratory methods. And another factor to consider is that the measurements obtained will often not be directly comparable to regulatory limits, as they are taken in field conditions, so it might be necessary to adjust for things like moisture content in the case of soil. The in situ measurements used in this example were acquired on the site of a medieval lead smelter, which was known to have a wide range of elevated lead concentrations. Here it is in Derbyshire in the UK with a horse on it. 24 sampling targets were included in the experimental design across the whole site. Note that this is not a complete square. The instrument was placed directly onto bare soil following turf removal. Sample duplicates were also acquired in a pseudo-random direction 2 meters from the primary sample. They also took core samples using a soil auger to a depth of 150 millimeters for analysis in the laboratory, and a second use of the core samples was to perform lab-based ex situ PXRF in order to obtain the analytical uncertainty of the in situ measurements of the PXRF machine. So I want to begin by looking at steps 1 to 6 from the VaMPIS flowchart. Here they are, and step 1, I'll go through these quite briefly, but step 1 will specify the measurand and the sampling target. The measurand is the total lead concentration by handheld PXRF, and the sampling target in this case was a square of side 30 meters. Step 2, identify the measurement procedure. Well, there were 24 sampling targets, applying the PXRF directly to the bare soil following turf removal. Step 3, design the validation. This was done by estimating the overall measurement uncertainty using ANOVA on a simplified balanced design, using sample duplicates acquired at a distance of 2 meters from the primary sample. Steps 4 and 5, while core samples were also taken in order to estimate measurement bias of the in situ measurements compared with the laboratory the in situ measurements compared with the laboratory measurements by ICP-AES. The core samples were also used to estimate the analytical uncertainty of the in situ measurements. So a measurement of a NIST reference material number 2710 and a statistically significant bias was found. For PXRF, the bias was about -11%, and for lab measurements using ICP AES, it was about -5%. Moving on to step 7 of the VaMPIS procedure, estimate MU. These are the estimates of measurement uncertainty from ANOVA for the in situ field measurements. And you can see the apparent uncertainty is estimated to be high at 77% for classical ANOVA. Further inspection reveals that the distribution of measurements is approximately log normal. So for this reason, the robust ANOVA values, which accommodates up to 10% of outliers, was used in the interpretation. A simplified balanced design was used to estimate measurement uncertainty in the study, which means there is no separation of the sampling and analytical components using ANOVA, but the analytical uncertainty from the lab-based PXRF on extracted samples was found to be 3%. If you subtract the variances, this gives a sampling uncertainty of 54.9%, so it's hardly any different. So we can conclude that the overall uncertainty is dominated by sampling uncertainty, and the analytical contribution is negligible. Alright, so looking at systematic uncertainty, or the bias between PXRF and a certified reference material was found to be in the region of 10 to 12%. But there is a very different physical form from the in situ measurements on field samples and the homogenized dry reference material. So it actually makes more sense to compare the in situ PXRF measurements with the laboratory measurements made ex situ on processed samples. In order to do this, we can use what's known as a maximum likelihood method of fitting a linear function where there is uncertainty on both axes. It's known as Fremel. From this plot we can see that there is a large rotational bias of around -40%, and so possible causes of this large bias include the following. It's likely that soil moisture is going to be the major factor. But anyway, how do we deal with this large bias? Well, we can either correct the PXRF field measurements using a simple calculation, and also with this method we could add the uncertainty of the correction into the random component of uncertainty from ANOVA, bringing the total MU to 58%. This approach effectively takes the measure around back to lead on a dry mass basis. Alternatively, we can add the bias and its uncertainty into the uncertainty from ANOVA. In this case, we would end up with a very large uncertainty of 98%. This would not be realistic or practical for the interpretation of these results, so we proceed with the validation, making the assumption that the bias will be corrected in the in situ measurements. So on to step 8 of the VaMPIS procedure, where we compare the measured uncertainty with the target uncertainty. In this study, there was no externally set target for lead in soil. However, for the purposes of geochemical mapping, a guideline criteria for fitness for purpose is that the measurement uncertainty should not exceed 20% of the total variance across the site. If it does, then it just obscures, it tends to obscure the variance, the actual variance across the site. For the purposes of comparison with a regulatory threshold, we can choose to use the optimized uncertainty approach to set a target uncertainty, and the next few slides will show this approach. So once again, we can use OptiMu program to calculate an optimal uncertainty. The costs of sampling and analysis were estimates based on the costs of labour and equipment hire. The threshold for total lead in soil was 2,000 milligrams per kilogram at the time of the study from the UK Department of the Environment. The uncertainty values which we have to input into Optima as standard deviations, can be calculated from the expanded relative uncertainties for sampling and analysis that you get from the ANOVA. The consequence cost for a false positive scenario is an estimate of the cost of unnecessary investigation and possible remediation at the time of the study. And finally, the concentration at which to optimise. In this case, we set it to 10% above the threshold, which is a concentration at which there is a reasonable chance that the measurement will be wrongly classified as above threshold. This is, again, of course, a false positive scenario. Now, step 9 of the VaMPIS procedure is to check whether the fitness for purpose criteria are achieved. Let's look at purpose 1, the purpose of geochemical mapping first. So using the target uncertainty of 917 milligrams per kilogram, which you may remember was 20% of the variance across the site, the total measurement uncertainty from ANOVA indicates that the method is fit for this particular purpose. The conclusion is supported by comparing the results of the PXRF survey, survey with a far higher density survey that used kriging, the technique of kriging, to produce a geochemical map. You can see that the highest PXRF measurements here actually correspond to the likely location of 2 smelters on the Krig map. Moving on to purpose 2, comparison with a threshold value. This is the optimization graph from the program. As before, the optimum measurement uncertainty and associated expectation of loss are shown at the top. And the optimal uncertainty, as before, is at the minimum of the loss function. The measurement uncertainty exceeds the optimal uncertainty by a factor of approximately 6. Consequently, this measurement procedure would not be considered fit for this purpose. Step 10 is to modify the measurement procedure to achieve fitness for purpose. Well, the high measurement uncertainty in this case is dominated by uncertainty from sampling. So using the information from stage 2 of the optimization process, it would be much more cost effective to reduce the sampling uncertainty than it would be to reduce the analytical uncertainty. So for example, the use of 4-fold composite samples at each sampling location would be predicted to reduce MU to about 23%. This would not be enough to achieve the target uncertainty, but this would require from sampling theory the use of 34 composites at each location, which would clearly be impractical. So the final step of VaMPIS is to review the fitness for purpose of the analytical method. This is only required for the sequential approach, but this slide gives some useful recap of step 9. So the current measurement procedure is fit for the purpose of geochemical mapping, that is for mapping the spatial distribution of lead concentrations across the site. But it is not fit for purpose of classifying sampling targets as being under or below or over the threshold of 2,000 milligrams per kilogram at this particular site. Now on a different site where there is less contamination, for example, all the sampling targets are below 500 milligrams per kilogram, which is much more typical, a measurement uncertainty of around 55% should be reliable against this threshold. Finally, we'll have a look at the applicability of this validation. We have seen how it is possible to validate an overall measurement procedure simultaneously, including all the sampling and analytical steps. At this site, the analytical uncertainty was negligible compared to the sampling uncertainty, which is partly due to the fact that the very high levels of lead concentration were well above the detection limit for PXRF measurements. This does mean that the validation is somewhat site-specific, which is often the case for sectors such as contaminated land. The validation in other sectors will be more generally applicable, for example, the validation previously demonstrated for nitrate in greenhouse-grown lettuce. In conclusion then, the example demonstrated the simultaneous approach to applying VaMPIS that is, including the sampling and analytical steps in an overall measurement procedure. In some cases, a particular measurement procedure can be fit for one purpose or some purposes, but not for others. And while it will not always be possible to achieve the optimal uncertainty calculated by the optimized uncertainty approach, this approach can be used as a decision support tool to assist in setting a target uncertainty, where this aims to minimize the overall costs, including the consequence costs of incorrect decisions that might be incurred. The optimized uncertainty approach, as we saw in the previous presentation, can also be used to apportion the costs of sampling and analysis in the most cost-effective way. Thank you. That is all.
Thank you, Peter, for your presentation, for all these application examples, and of course for the OptimView. There is a question where the people can find that software. I have a QR code at the end of the presentations, but is available in the Royal Society of Chemists, or when we can download this software.
They will all, but also be available on the video, will they not?
Okay. Okay.
Yes, on YouTube.
On YouTube, yeah.
Great. Great. So we have some time. If there is any question, you can ask, of course, in chat. But we are running fast now, so we have some minutes. If you would like to ask something in the chat, please now, in order to avoid noise interferences. Now we are continue on the managerial part of the VaMPIS and the sampling. The next the next session and is a joint presentation for Patricia and Vasilis, is for management of the whole process, measurement process, including following up after the validation. So the two presenters are Dr. Patricia Stefanelli, is researcher at the National Institute of Health Exposure to Air, Soil and Lifestyle Contaminant Unit in Rome, Italy. He has 30 years experience in both research and regulatory activities in the field of environmental exposure to contaminants, in particular pesticides residue in different matrix, with advanced level in analytical chemistry skills. His main responsibility are creating, developed and validation methods for determination of pesticides residues in food at the National Reference Laboratory for Pesticides Residue, and activities related to the national monitoring of official control of residues in food. She holds multiple positions at various working groups and advisory boards. Sorry, Peter, you have not unshare your screen, so please unshare your screen in order to Patricia and Vasilis share the new screen. The second presenter is Vasilis Zonaras, works in the pesticide residue laboratory for Benaki Phytopathological Institute at the National Reference Laboratory for Pesticides and Food and Feed in Greece, dealing with GC amendable pesticides, GC-ECD, GC-FPD, GC-MSMS. He has experience in development validation method, analytical method in accredited laboratory using high technology instrumentation. Previously worked in a QC and R&D labs in pharmaceutical industry. So, Vasilis and Patricia, the floor is yours.
Thank you, Marius, for the introduction. Hello, everyone. I'm going to share my screen now.
Great.
Can you see the presentation? Okay. Okay, so two sections of published guide are going to be presented. The first one is section 3, follow-up after validation, with the subsections integrated measurement quality control We will see what are the objectives and when this is applied. The participation in sampling proficiency test as part of the external quality control and the evaluation of qualification of samplers. Afterwards, Patricia will present section 4 of VaMPIS Guide Management Issues with the subsections Sampling Standard Procedure, Responsibilities, and Communications. It is well known that the validation of measurement procedure provides objective evidence that the selected measurement procedure is fit for a specific purpose, while the ongoing validation ensures that the measurement procedure remains valid during routine use and that's still fit for purpose. The ongoing validation includes the routine monitoring of a measurement procedure and covers all the factors from the sampling and analytical part that may influence the performance of the measurement procedure, as well as the evaluation of the performance of the measurement procedure after one or more changes have been made in the sampling or analytical part since the initial validation. For example, when new equipment is used or when method improvement has been carried out. The requirements of the ongoing validation should be the same or close to those of the initial validation. It should be performed according to an approved procedure and well documented. To ensure fitness for purpose for routine measurement procedure, we established the integrated measurement quality control plan that includes both sampling and analytical part. It is noted that the analytical quality control is performed by replicated analysis, while the integrated measurement quality control uses replicated samples in addition to replicated analysis. So in that case, we estimate the overall measurement uncertainty and the components of the measurement uncertainty, that is the sampling uncertainty and the analytical uncertainty individually, and then compare these values against the initial values. We also check if there is contamination by analyzing blank field samples and check the stability of the analyte by analyzing spiked samples. Now, when a parameter of sampling or the analytical part has changed, then we have to check whether these changes affect the initial performance. And the key metric for that is measurement uncertainty. So we recalculate the measurement uncertainty value after applied a simplified balance design. And then we compare this value against the initial value. If the new value is not significantly different from the initial value, then we can state that the method is still fit for purpose and the original value can be reported. Otherwise, the overall measurement procedure should be validated. The integrated measurement quality control demonstrates that the overall measurement procedure is adequately controlled and fit for purpose. So it should cover the primary sampling, the physical preparation of the primary sample, and the analytical procedure. The objectives are the monitoring of the overall measurement uncertainty and its components, sampling uncertainty and analytical uncertainty, the monitoring of the sample contamination, and finally monitoring of the stability of primary samples. It includes both internal and external quality control. During the internal quality control, we may use reference sampling targets, reference materials or quality control samples, working test materials, and construct control charts, or perform within laboratory comparisons. During the external quality control, a laboratory may participate in collaborative trial in sampling or in sampling proficiency test. But when an organization performs only sampling, the question is, can perform validation or can apply the integrated measurement quality control? The answer is no, because it cannot provide quantitative results such as monitoring of the measurement uncertainty. In that case, this organization should collaborate with the testing laboratory in order to undertake both the integrated validation and the subsequent integrated measurement quality control. As it was mentioned before, a laboratory may participate in a sampling proficiency test as part of the external quality control. That is a measurement proficiency testing scheme. In that type of proficiency test, the participants perform replicate of the overall measurement procedure: primary sampling, physical sample preparation, and chemical analysis. Now we can see an experimental design of a sampling proficiency test. The results of a sampling proficiency test can be used for the training of new samplers, the certification of samplers, and the accreditation of sampling organization, for example, according to ISO 17025. But also, these results of the sampling proficiency test can be used for the estimation of sampling uncertainty that includes the systematic effects between different samplers. So in that case, we compare this new value against the initial value of sampling uncertainty. If the new value is significantly different from the initial value, then the sampling procedure should be reviewed or tested in a further sampling proficiency test, or the method validation should be reviewed or reevaluated using the new sampling uncertainty value. But why laboratories should participate in an integrated measurement proficiency test? It is noted that analytical proficiency test schemes usually utilize relatively homogeneous materials that do not need further processing or subsampling. So in that case, the estimates of measurement uncertainty are likely to be underestimated because components that could usually arise from a field sample, for example, chopping, drying, and homogenization, are ignored. On the other hand, the sampling proficiency test includes replication of all the procedures that would be used for a real field sample. So the results of a sampling proficiency test are obtained from measurements made on realistically heterogeneous sampling targets, ideally in field conditions. And for the end, a few words for the ongoing evaluation of samplers. Their performance and their qualifications are monitored through the integrated measurement quality control system. So the samplers should have knowledge of the basic principles of sampling techniques. Terms like measurement uncertainty, they should know how to control and calibrate the equipment used, and also be aware of all the factors that may influence the validity of the sample. Their performance and their qualifications should be evaluated routinely, for example, every year through the ongoing specific surveillance process, providing quantitative and descriptive performance data. During the ongoing evaluation of the samplers, the other parameters that should also be considered are, for example, changes to the relevant standards and regulatory requirements, as well as the ongoing changes in technology. This is the end of the first part. Thank you for listening. Now Patricia will continue with section 4, management issues. Thank you very much. Patricia, the floor is yours.
Thank you, Vasily. And just a moment to share my presentation. Can you see?
Yes.
Okay.
Yes, very clear.
Okay,
Yes.
now I'm going to present the section 4 of VaMPIS guide, the management issues. Which are the keywords of management issues in VaMPIS guide? One is the chain of custody, but also the sampling procedure, the cooperation and communication, and finally, training and responsibility. Chain of custody needs to be established much more for logistical rather than methodological traceability. As the sample is based on one or more people being responsible for the various steps of the entire measurement process, it's clearly important that the role of each person is defined, determined before starting the process by the identification of responsibilities. Who is responsible? Ideally, the laboratory manager, who delegates responsibility to relevant people who are involved in the various phases of the process. And could be both internal or external stakeholders. As the sub-responsibility can vary depending on circumstances, it could be useful to specify the area of responsibility in advance by using a responsibility matrix. Here, one particular example, a case study, of this kind of matrix. Here, the sampling is performed by the laboratory, so the laboratory manager is overall responsible, sharing some responsibility with other people with regard to the different measurement phases. About for instance, the last phase, the quality of the final measurement results, the laboratory manager share the responsibility with client here because the client is co-responsible of the primary sampling with the laboratory. But this is an example. The tip here is to use this kind of framework to highlight, to map the area of responsibility in advance. Sampling standard procedure. All steps of the sampling procedure should be identified and documented to ensure the validity of the entire process. Of course, after verification that the procedure is fit for use. Scrolling on the section 4 of VaMPIS guide, the minimum information to be stated with the sampling procedure are listed. Here are reported only the first 6, but many information should be reported in the procedure. In any case, any relevant information and any substantial deviation from sampling procedure should be described in the sampling report. When a sampling procedure has been established and validated externally by a regulator or similar, the sampling or measurement team has the responsibility to follow the procedure, the document, and apply the integrated measurement quality control as appropriate. So the designers of the sampling must be a people with the knowledge and experience about sampling target, about the purpose, about the form and conditions of sampling. One more relevant keyword in the management issues of VaMPIS guide is the term training. The training is important for all steps of the entire measurement process. Here is highlighted for the phase of sample handling, transport and reception at testing lab. So whoever is responsible for these steps should be sufficiently trained about the deterioration of samples, about technical guidelines, regulations, recommendations or similar. But also samplers should be trained. Useful for staff to have specific instruction, such as a written standard procedure. In this case, for checking or rejecting the sample at the reception. Cooperation. There needs to be ongoing cooperation and collaboration between parties, especially when the sampling and analysis are carried by 2 or more different organizations. Prior to scheduling the sampling, all relevant information should be shared between the laboratory, the sampling staff, and also between the client. The tip here is that the sampling organization and testing laboratory should collaborate to achieve reliable measurement results. And finally, communication. The communication phase could be divided in 2 different steps. A preliminary stage using an informal communication, a mobile phone, and one more official formal communication, for instance, a written communication. The initial communication stage could identify requirement for additional training or modification of the technical procedure within the sampling procedure, including transport and storage. The samplers need to frequently contact the laboratory and sometimes also directly the client. This approach is particularly significant in case of sampling activities are performed by 2 or more organizations. All in all, good communication is essential in case of independent organizations. including sharing information about to estimate measurement uncertainty and consequent judgments on fitness for purpose. To sum up, the section 3 and 4 of VaMPIS guide discuss and try to give answer about some specific points, about some specific needs. The need for ongoing quality control of the whole measurement process, in terms of integrated measurement quality control, in terms of including quality control of both sampling and chemical analysis. The need to improve coordination and communication between laboratory and samplers. This point has been and will be important before, during, and after VaMPIS, because traditionally sampling has been often undertaken by separate organizations. This specific approach, this traditional structure makes implementation of VaMPIS a challenge. So my colleagues and I, we conclude the presentation of section 3 and 4 of VaMPIS guide. Thank you for the attention.
Thank you, Patricia, for your presentation, and Vasilis. It was a very interesting presentation about, except for the scientific part of measurement uncertainty, but what happens also in managerial part of all the process and how important is the communication between the organization, especially in cases that we have different organizations that take place, the sampling in different organizations that do the analysis or more. So here was Patricia and Vasilis was the last presentation for today's webinar. We have plenty of time for questions and a discussion. So I encourage you to write if you need any question to chat box, or if someone now needs to add a comment or ask a question orally, please ask us in chat box and we will give the place in order to answer to do the question that need. So would you like, the presenters, would you like to add something or to make a comment, someone of the presenters, about all this presentation today, until the participants do their questions? Mike, would you like to add something?
I hope that people have seen that, the point that you made, it isn't just a scientific procedure, VaMPIS. It does require a change of mindset. For hundreds of years, samplers and analysts have not talked to each other much and have worked in separate ways with separate quality systems. And what's needed here is a coming together. So it's going to take time for us to reorganize ourselves so samplers and labs work more closely together. But the umbrella of ISO 17025 in a way encourages us to do that. And what we hope is obviously that this guidance gives us a framework within which we can work together to ensure the quality of measurements and hence the quality of the sampling.
Yes, I agree with you at all, Mike. Yes, this is the new challenge to incorporate together the organization of sampling and organization of analysis. I don't know, Fernando, if you would like to add something about the regulatory part of that, and how important is also the regulation to encourage this communication of these two organizations, the sampling and analysis part.
Can you hear me?
Yes, very clear.
I don't see myself. I have my
video.
We
can see you. We can see you.
Oh, I cannot see myself. I don't know why. Well, anyway, in fact, I answered to one question for one or two questions already concerning food contact materials. But what I want to point out is that from the regulatory point of view, from accreditation requirements for testing labs, sometimes I'm surprised with the fact that if the ISO 17025 has been written in 2017, I think the latest version, where it says the section dedicated to sampling, all these requirements. And I'm always surprised why there is still a lack of recognition that sampling is, that's why we need these guides in Eurachem. So it's one thing is what the international standards says, what the international standards requires, and the other thing is what in practice what laboratories do. And what laboratories do sometimes is taking the easy, the shortcut, saying that, well, I believe that the customer, whoever it is, brought me samples who are highly representative of what I want to measure. So it means my duty is analyzing, and that's it. And this, I hope this will change with some time. These things take time. But I hope I'm optimistic that more and more with this contribution from the Eurachem, with this extra guide, that people start, quality managers, quality teams, laboratory managers, and so on, with accreditation bodies, regulatory bodies, they all start as I wrote down. I'm always optimistic and say, well, it will take time, but people will understand that sampling is also, maybe I disagree that people say sampling is always the most, the larger contributor to the measurement service. Well, it depends what you are sampling. You have to use always common sense, your experience. Sometimes if you are imagining, I just give you an example, if your sample target is a well-controlled food process by a company with a competent quality management, well, the samples that you take over in these food processing stuff cannot be very large, has to be controlled already by control charts. So it depends. It depends. The same evidence when you go to a field, and no matter agriculture, for instance, I did that for 3 years. If you go to a field organic, certified organic farmer, they have so much control by external auditors just to maintain their certificate of bio farmer, that of course there is a history. They know when we go to these fields, we have already a history of measurements, and we know what's the variability that we may find down, which means that it's not difficult to plan a composite sample which takes a quite representative sample. So it's not, I disagree with the negative idea that the sampling is a huge contribution, but it depends what you are measuring. And I hope that people will start using their experience to realize that, well, I cannot from now on never more ignoring the sampling component of the overall measurement certainty.
Yes, thank you, Fernando, for your comments. I agree with you. Sampling is not easy, and it was not easy, but it's not something that is impossible. So there are some tools. There is the guideline now. We can, of course, all the guidelines are become more and more changing and based on the new things that come up with the years. So yes, the important part is to look about the sampling, not leave it to the behind and say, okay, I'm only for analysis. And of course, the much more important stuff that Patricia and Vasily said about the communication. So let's do a question just because we have not yet some come up in the chat box.
Okay,
yes, of course, Peter. Yes, please.
I was saying, I noticed there are a couple of questions about how to get the Optimu and the Renova software, and it's somewhat unfortunate timing. But I know that the AMC have been migrating to a sort of new website platform, so they're not in the usual place. I don't know, Mike. Do you know anything about what's happening there?
No, I think it's still in transition, but we have some QR codes.
Yes.
I think Marios is going to show them.
Yes, and I will share now. I was expected to do later, but I can share now in order to have that QR codes and check it.
And
Okay.
there's one
I mean, if
QR
necessary,
code.
I have managed to find a link to a web page that does have that software on it. So, but we'll see if the QR codes work, perhaps.
Just give
You
me a
do have a bit
moment.
of difficulty with that because I think the links that you had a week ago are probably no longer valid.
Yeah,
Give me
that's what I was wondering.
Yeah, me too. And I can't find the Analytical Methods Committee on the members area.
I mean, I have just found when I typed in basically ran over AMC software, I did find a page where those links are there, including Optimu, but I don't know how long that'll be there for.
Right.
So,
well,
can you see my screen, full screen?
yeah.
So here is the QR code of the guideline, the VaMPIS from Eurachem site. The OptiMU, we will run now a check in order to see if it's available to you, or please check all of you to see if there is any problem with the OptiMU.
Yeah, that just takes you to the General Community and Networking page. It's been redirected.
Okay.
I'm afraid the Royal Society of Chemistry have changed their website too much very recently, and that link is no longer valid.
So,
yeah, so the Optimu link doesn't work.
I am trying to find the correct link now, but what we'll try and do is once we do find it, we'll include it somewhere in the presentations on the Eurochem website, or more likely, add it to the Eurochem reading list and on the Sampling Uncertainty Working Group page.
Yes.
So we'll try and update any links on the Eurochem website to these.
Okay. We will inform you about that. Our apologies about that change. Don't worry. But you have our communications path through the Eurachem, and of course, all the presentation will be uploaded in the Eurachem site. We have also the QR code in order to check for the guide and the leaflets. And of course, there, since they were uploaded, we will have also the new link from the OptiMU. Also, the presentation will be uploaded in the EUROLAB site. So, for your questions before in chat about the presentation will be uploaded from in both of sites, Eurachem and EUROLAB. And of course, you can check YouTube channel with videos of previous presentation, and also this webinar will be uploaded here. And don't check to look at our LinkedIn that we uploaded news about the webinars, the leaflets, the guidelines, or different trainings that we run as a Eurachem part, and of course the Eurachem site. Every webinar is not important if we have not your feedback. So here is the QR about the feedback and for your certificate quests. You can use the QR code to use it, and I will also upload the link in order to have it in the chat box in order to leave your feedback for the event in order to become better, or some news that you would like to learn about it. We have some time for the questions. Here, sorry, I haven't checked the chat box.
Can you leave the feedback and certificate QR code up for a bit longer?
Of course, yes. Here we are. Just a moment.
For those of you who are looking for the RSC Analytical Methods Committee software page, the link is now in the chat.
There is a comment. Yes. There are two comments, two questions. I will in the chat box. Of course, thanks for the speakers. The effort are very appreciated. I do hope to will catalyst. Okay. So another question is, if an accredited lab is not in a position to dictate for clients how to conduct sampling, is it possible to report that analysis is conducted conducted of the sampler that is sampled by a client, and still the lab maintain the accreditation? This is a question for Samia. I think, is anyone that would like to answer that? I think that this is accreditation body part responsible, and depends on how the laboratory is responsible for sampling or not, or for analysis. I don't know if someone would like to add to that from the speakers.
Fernando, could you comment on that?
Well, in general, traditionally, accreditation bodies, they come every year, and I was doing that for decades, answering to their questions and trying to solve the problems that they were putting in terms of a measurement procedure. And normally, unfortunately, as we have said already, they were somehow ignoring the sampling component. So it means that when a lab receives a sample from a customer, remember that the customer could be even a regulatory body. So could be a regulatory body that took a sample that needs to be analyzed to decide for a conformity. So remember, so it's not a normal customer. And of course, the laboratory has nothing to lose in terms of their accreditation, because accreditation is more focused on the analytical part of the measurement procedure, not on the sampling. This is what has to be, as I said, we all try to convince accreditation bodies and regulatory bodies that from now on, they should not ignore that there is a contribution of measurement certainty coming from a certain variability coming from sampling. And this has to be started, and the collaboration between both. But no, never. The laboratory do not lose their accreditation for a certain measurement procedure just by the fact that reports, well, we analyze the sample as received by the customer, because they trust the customer work, you see? So no, there is no, but hopefully this will slowly change to a laboratory manager asks for the sampling plan, the sampling methods, and they start collaborating with each other to try to improve the situation. There is a person who wants to take over.
Yes, of course. Primoz, if I said correct, please. You can speak. I think you can open your microphone, and can you hear us, or have you write something to the chat? No. Can you hear something?
Maybe he or she can write down.
Yes. Praise. So, Primoz, can you hear us? You can speak? Yes. I see that you are.
Primoz Auersperger from Slovenia, from water company of Ljubljana, and also assessor of Slovenian accreditation. Here in Slovenia, we have one guidance, OA03, which deals with exactly this measurement certainty of sampling, and that's all very similar with duplicates. But I have one comment regarding it's very important to address that collection of parameters for evaluation of sampling uncertainty is crucial, because the parameters must be measurable. So this is expected higher than 10-fold of LOD. This is some very good address, because in such a kind, it is possible to combine a relative standard deviations of these 8 duplicates. So only that.
Okay. Thank you.
Our guidance is also in English, OA03, It can be found by Google search Slovenian accreditation OA03, and you can find in English.
Thank you. Thank you for your information.
Okay, goodbye.
Thank you. Thank you very much. Yes, is
You're
someone that
welcome.
would like to add something from the speakers, comment in the previous?
I think an application in the water sector is going to be discussed at the IMICO conference in September. Natalie, I think, is going to give a presentation
Yes,
where she's been applying the duplicate method in the water sector and comparing it with other techniques. So watch out for that. That's I don't know whether we can. There is a link to that IMICO conference in September.
IMECO, the IMECO conference,
Yeah.
correct?
Yeah. I don't know if I can. I could maybe find the link for that.
Yes. We have also another comment from Alenka.
Yes. Hello, everybody. Can you hear me?
Yes. Very clear.
Hi. I would just. I come from an accreditation body, and I'm the lead assessor. And I would like to confirm what Mr. Fernando was explaining before. So there is a requirement in the standard in the in 7.8, which describes the requirements for reporting. So the laboratory can only report the results that come under their responsibility. So if the laboratory is not responsible for the sampling, this has to be mirrored in the report. And there is a specific clause. I cannot remember now from the top of my head, but it says that the report has to clearly state whether the results apply to the sampled or tested items. So this is the distinction, and all the reports have to have this comment somewhere included, and we distinguish between those. So if the sample, if the results apply to the sampled item, then this means it will incorporate the whole measurement procedure, including sampling, and we conclude from that that the laboratory also performed the sampling. Whether, on the other hand, if the laboratory only performed the analytical part, then they will only claim that the results apply to the items tested. So this is the indication of the responsibility of the laboratory, and I'm not sure about other accreditation bodies, but I also come from Slovenia, like pretty much before. But we absolutely take this in consideration, and we also require, if the laboratory is responsible for the sampling, we search for the information on what kind of population. So the population that the results apply to has to be defined somehow in the report. We think this is also very important. So,
Thank you. Thank you very much. It's very important that is not something, the communication, and also it's something, because sampling is very important in many cases, but the client doesn't know that. It's important to also the clients learn, but in many cases, because the client looking for the costs, it's not easy always for the laboratories to prove their states or to have a good communication that is important in that stuff. Not only just behind the two organizations from sampling and the laboratory, but also for the clients, that they have to learn that in order to have reliable results, we need also the sampling in many cases. Thank you, Alenka, for your comment. Is any other? Let's check a little bit the chat. So far, there is no any other comment. If I missed something, please tell me. I think the time goes very close to close our meeting. Please again check If you need, give us your feedback, and if you need a certificate, please check the QR code. Also, if you are interested to learn more about the VaMPIS guide, there are a lot of QRs about there is the QRs from VaMPIS guide. In Eurachem side, you can find more material about general for measurement uncertainty, method validation, traceability, and many more stuffs about the analytical measurement general. In our YouTube channel in Eurachem, you can see more webinars in different topics, and of course the LinkedIn. So far, thank you very much to all. If the speakers would not add something, I don't know if from EUROLAB need to do some comment or something else, or the speakers to add something. I think we are ready to close the day.
Marius, can I say something quickly about the
yes.
certificates?
Yes.
If you ask for a certificate after filling in the feedback form, and I can see that some of you have, if you don't find your certificate in your email within about 10 minutes, first, please check your spam traps, because that's what usually happens. Then, if you really can't find it, or if you have made a mistake and your name is not properly appearing on the certificate, then I'm going to put an email in the chat that you can follow up with. You'll also see it, I think.
Events.
You can see the events at Eurachem.org address on the screen.
Yes.
Then you can ask it in really serious problems. Try that email address. I won't guarantee that it will be answered immediately, but I will try and follow up problems if I can. This is being run on a bit of a shoestring though, so I'm not gonna offer an instant service.
Okay, thank you, Steve.
That's the email address for problems with certificates that simply don't arrive. The other thing you can try. The other thing you can try, by the way, if you submit once and you've made a mistake getting your name correct on the certificate, and that does happen to all of us, clear your browser cache, because the check relies on cookies. So either change browsers, change machines, or clear your browser cache, and you can have another go at the form. So
thank you.
Before you email us, please.
Great. Thank you very much for technical information, Steve. And thank you all that attended.
I'd just like to reiterate the people who asked about access to AMC software, whether it's the Ranova program for doing the balanced design or the Optimu. Steve has added a fresh link to the chat, so pick up that fresh link before you log off, and people can get access to that software. I'm sorry for the fact that
I've done one other thing as well. If you go to the Eurachem website and look at the sampling uncertainty working group page, you will also find a link to the software there.
Oh, that's good. Thanks, Steve.
The only thing is you may have to register to get to it.
Okay. Any other comments from the presenters or the attendees, participants? Okay. Yes. Yes, Eugenia.
Eugenia's.
Yeah, thank you, Mario. So I would like to thank you very much to all our attendees and to our valuable presenters for a very interesting and very good webinar with a lot of practical information from our side. And as Steve mentioned and Mike mentioned just a few moments before, we are waiting you on our Eurachem website, okay, for you to access the information regarding VaMPIS. Okay, and don't forget to fill in the feedback form. Okay. Thank you very much to Mario for moderating.
Thank you. Thank you also, Maureen, for all this technical part behind the Zoom. And of course, Laura, thank you for the cooperation that continues to be always very good with EUROLAB.
Indeed.
Thank you.
Thank you.
Thank you, Laura.
I'm stopping the share, so I think you will leave to have a nice evening, or every time you have in your country. Good. Have a nice summer. Bye.
Okay.
Thanks, Mario.
Thank you very much,
Bye,
all.
everyone.
Thank you, Laura. Thank
Bye,
you,
everyone.
Maureen. Bye.
Bye, everyone.
Bye.